Picture a modern corporate fortress, but instead of stone walls and iron gates, it's under this invisible, constant, silent siege.
Right. It's happening 24/7.
Exactly. Like right now, this very second, there are just millions of data packets slamming against the digital perimeter. It's this relentless automated barrage launched by, botnets and threat actors from literally every corner of the globe.
And they never sleep.
No, they don't. They are probing for just a single open port, a single misconfigured routing table, or maybe a forgotten legacy server. And the terrifying part, if even one single malicious packet slips through that invisible wall, if it's carrying the right payload, an entire company's infrastructure could be totally compromised.
I mean, we are talking about critical databases encrypted and held for ransom.
Right, or intellectual property just siphoned off in the dark. Or a total digital blackout that brings a multi-billion-dollar operation to a grinding halt. So the question we are exploring today is this. When the invisible siege begins, what exactly stands between your organization's most sensitive data and absolute catastrophic failure?
It's a high-stakes scenario, and it is not hypothetical. That silent siege is playing out continuously. It's the baseline reality of the landscape modern IT professionals are walking into.
Yeah, and if you are ready to take control of your career and, really understand the real-world tech demands of modern business, make sure to like, subscribe, and share this deep dive so you never miss the insider tips that could one day save your career.
Absolutely.
Also, definitely check the description for access to additional high-value resources. Now, to give you some context on where we are in our journey, this is the 13th of 14 deep dives based on the textbook Hands-on Ethical Hacking and Network Defense, 4th edition by Wilson, Simpson, and Antill.
Right, we're getting near the end.
We are. And in our last deep dive, we covered Chapter 12. We unpacked cryptography and those mathematical algorithms used to scramble data to protect its integrity in transit.
And cryptography is essential, obviously. But as we discussed, encrypting the payload is really only one piece of the puzzle. You can have the most secure safe in the world. But if you just leave it sitting on your front lawn with no security cameras or fences...
someone's just going to load it into a truck.
Exactly. Eventually someone will find a way to break it open or just steal the safe entirely.
Which perfectly sets up our mission today. In this deep dive, we are covering Chapter 13, which is Network Protection Systems. We are moving from the cryptography of the data itself to the literal architecture of defense.
And this is an area where my background as an independent industry analyst really intersects with the material.
Oh, for sure.
Because I spend a significant amount of time evaluating academic programs, curriculum pathways, and industry readiness. And looking objectively at Dr. Schuessler's Ethical Hacking and Cybersecurity Operations course, it is remarkable how effectively this specific curriculum bridges undergraduate academic insight with the grueling high-pressure demands that early career professionals are going to face.
It's the real-world stuff.
Right. We aren't just talking about abstract theories today. We are talking about the actual hardware, the specific configuration syntax, and the operational mindset you need to build a network that can withstand that siege.
I love that. Our objectives for this deep dive are incredibly tactical. By the time we are done, you will understand how enterprise routers and firewalls function, the specific tools and commands used to configure them, the critical role of intrusion detection and prevention systems.
And the human vulnerability.
Yes,
Right.
The human vulnerability addressed by web filtering, and honestly, my personal favorite topic, the psychological warfare of honeypots. So, to defend the fortress, we have to start at the perimeter. Let's talk about unified threat management and the power of routers.
Well, when we use the term network protection system, we are really talking about any device or software designed specifically to safeguard network traffic.
Okay.
Historically, this meant a very fragmented approach. You'd purchase a firewall from one vendor, an intrusion detection system from another,
A VPN box from someone else.
Exactly. A separate appliance to handle your VPNs, and yet another server just dedicated to filtering out malware.
I can imagine the management overhead on that was an absolute nightmare for an IT team. You've got 4 different interfaces, 4 different licensing agreements.
And you have to somehow make sure they're all talking to each other.
Right. Without creating massive bottlenecks.
It was a logistical nightmare, and it introduced massive latency. Every time a packet entered the network, it had to be handed off from box to box to box.
Being inspected at each stop.
Right. That is why the modern enterprise environment relies heavily on UTMs, or Unified Threat Management Devices.
Like an all-in-one deal.
Exactly. It's an all-in-one security appliance. It combines the firewall, the VPN gateway, the IDS and IPS functionality, and the malware filtering into a single high-performance piece of hardware.
It has to streamline things massively.
It radically streamlines administration. You are managing one unified policy engine, which is a highly sought-after operational efficiency in corporate environments.
But before we get to the complex filtering engines of a UTM, we really have to talk about the fundamental building blocks of network traffic management, the enterprise routers.
Essential hardware.
Right, and I think there's a dangerous misconception here for anyone just stepping into the field. Like, when I say router, the average person pictures a little plastic box sitting next to their TV that pushes Wi-Fi to their laptop.
Oh, absolutely.
But in the context of enterprise cybersecurity, that is a completely different universe of hardware.
Completely different. What's fascinating here is the sheer scale, the processing power, and the responsibility of enterprise routers. We are talking about heavy-duty, rack-mounted hardware devices that cost tens of thousands of dollars.
Wow.
Their primary purpose is to direct massive volumes of packets to different network segments at line rate.
Line rate meaning?
Meaning without slowing down the flow of traffic at all. They segment networks to prevent broadcast traffic from flooding every machine in the building. And most importantly, they choose the most efficient, secure paths for moving those packets across complex global infrastructures.
They are like the ultimate air traffic controllers of the internet.
That's a great way to put it.
And they don't just guess which wire to send the packet down. They use very specific mathematical algorithms. Right. The routing protocols.
Yeah, to build their maps.
The textbook outlines three main types. I want to dig into how these actually work, because understanding how traffic flows is the first step to manipulating it as an attacker or securing it as a defender.
Absolutely.
Let's look at link state routing protocols first.
So a link state routing protocol, like OSPF, which stands for Open Shortest Path First, is highly intelligent and efficient. Instead of constantly broadcasting everything it knows, a router using a link state protocol acts more like a surveyor.
Okay, a surveyor.
Right. It only sends out link state advertisements to its neighboring routers when it discovers a new path, or when an existing path goes down.
Oh, I see.
It uses algorithms, like Dijkstra's shortest path algorithm, to independently calculate the best route to every destination based on the speed and reliability of the links.
So if a fiber optic cable is cut by construction workers on the east side of the campus, the router nearest to that cut immediately detects the dead link.
Then sends a quick surgical update.
Right, saying to the other routers, hey, the east link is dead, recalculate your maps. It only advertises the change.
Precisely. It conserves massive amounts of bandwidth because it isn't constantly yelling its entire map over the network.
Makes sense.
Contrast that with the distance vector routing protocol, like RIP, the Routing Information Protocol.
RIP.
Yeah.
Yeah.
Distance vector is an older, much more verbose way of doing things. If a router uses this, it periodically passes its entire routing table to its immediate neighbors.
Wait, its entire map? Every time?
Every single time.
I imagine if I'm an attacker who has managed to get a foothold on a segment of the network, a distance vector protocol is an absolute goldmine.
Oh, it's a massive vulnerability.
Yeah, because if the router is just blindly broadcasting its entire map of the network every 30 seconds, I could just sit there with a packet sniffer, quietly listen, and suddenly I have a complete architectural blueprint of the corporate infrastructure.
Without having to actively scan or trigger any alarms.
That is wild.
That is a brilliant observation, and it's exactly how an ethical hacker approaches network reconnaissance. Passive listening to chatty routing protocols is a classic intelligence gathering technique.
So they just wait for the router to spill its secrets.
Exactly. Furthermore, distance vector protocols are prone to catastrophic misconfigurations like routing loops.
How does a routing loop happen?
Well, imagine router A thinks the fastest way to the database is through router B. But router B's table gets corrupted, and it thinks the fastest way to the database is back through router A.
Oh no. So they just play ping pong.
Exactly. A packet destined for the database arrives. Router A sends it to router B. Router B sends it right back to router A. The packet bounces back and forth at the speed of light.
Consuming all the bandwidth.
Yes.
Yes.
It effectively creates a localized denial of service attack just from a simple logic error.
That's terrifying.
Link state protocols have mechanisms to prevent this, but older distance vector setups are highly vulnerable.
Okay, so that brings us to the third type, the path vector routing protocol, Where does this fit in?
Path vector protocols, specifically BGP, or the Border Gateway Protocol, are the backbone of the entire Internet.
The big leagues?
Exactly. While link state and distance vector are used inside a corporate network, what we call interior gateway protocols path vector is an exterior gateway protocol.
So it connects the big networks together.
Right. It dynamically updates paths to transmit packets from one massive autonomous network, say an internet service provider in New York, to an entirely different autonomous network in London.
Okay, so it's global.
It is. It doesn't just care about the shortest distance. It cares about complex rules, commercial agreements between ISPs, and massive scale routing policies.
Understanding that flow is critical, but knowing the anatomy of the specific equipment directing that flow is what really separates a novice from a highly paid professional.
Absolutely.
You evaluate these career pathways constantly. In Dr. Schuessler's course, there's a heavy emphasis on Cisco router architecture. Why Cisco specifically?
That's a great question.
And why do early career professionals need to know what physical chips are inside the box?
Cisco remains foundational to enterprise networking. While there are other major players out there like Juniper and Palo Alto, Cisco's architecture, their command line interface, and their underlying logic form the baseline language of modern networking.
It's the industry standard.
Exactly. You cannot just memorize definitions of routing protocols. You need to understand how the hardware actually processes and stores those protocols. If we connect this to incident response, a responder needs to know exactly where the volatile data lives versus the persistent data.
Let's pop the hood on a Cisco router then. We know what RAM and ROM do in a standard desktop computer, but a Cisco router utilizes its memory components in a very specific proprietary sequence. Let's look at RAM first.
So, in a Cisco router, RAM, or random access memory, is the operational workspace. It holds the active routing tables, the packet buffers, and most importantly, the running configuration file.
The running config.
Yes. This is the exact set of instructions the router is executing at this very millisecond. But the critical vulnerability of RAM is its volatility.
Meaning if it loses power.
If the router loses power, resets, or crashes, every single piece of data in RAM is instantly wiped out.
Which means if an IT admin has spent 4 hours painstakingly typing in complex security rules and the building loses power before they save their work, it is entirely gone.
It vanishes into the ether, and that highlights the absolute necessity of the next component, which is NVRAM, or non-volatile RAM.
So NVRAM is the backup.
NVRAM acts as the secure vault for the router. It holds the startup configuration file. Because it is non-volatile, that data survives a power loss.
Okay, so it's safe in there.
Right. When a Cisco router boots up, one of its final steps is to pull the startup configuration out of NVRAM and load it into the volatile RAM to become the active running configuration.
So RAM is the whiteboard you are actively drawing on, and NVRAM is the filing cabinet where you lock away the finalized blueprint at the end of the day.
That's a perfect analogy.
If someone wipes the whiteboard, you can always go back to the filing cabinet to restore the plan. But what about the operating system itself? The router needs an OS to even know how to read the NVRAM, right?
That is where flash memory comes into play. Flash memory is rewritable, non-volatile storage that holds the Cisco Internetwork operating system.
The iOS image.
Yes.
Right.
This is the core software that makes the hardware function. Because Flash is rewritable, network administrators can perform remote upgrades to the iOS.
Oh, nice.
Yeah, so if a new zero-day vulnerability is discovered in the way Cisco handles BGP, administrators can download a patched iOS image into flash memory without ever having to step foot in the data center.
So they don't have to swap physical parts.
Exactly.
And finally, we have ROM, read-only memory. If Flash holds the main OS, what is ROM actually doing? Is it just a basic BIOS?
It acts similarly to a BIOS, but with a critical emergency feature. ROM contains the power on self-test and the bootstrap program that initializes the hardware.
Standard startup stuff.
Right. But it also contains a stripped-down minimal version of the Cisco iOS, sometimes called ROM monitor or ROMMON mode.
ROMMON mode?
This is your absolute disaster recovery safety net.
Give me a scenario where an IT professional would actually need to rely on ROMMON mode. Like, when does things get that bad?
Let's say a junior administrator is attempting to upgrade the iOS image in flash memory, and right in the middle of the file transfer, the network connection drops.
Oh, the image gets corrupted.
Yes. When the router restarts, it looks in flash for the OS, finds a corrupted file, and fails to boot.
It's just a $30,000 brick at that point.
Exactly. But instead of staying dead, the system automatically falls back to the ROMMON mode stored in ROM.
Oh, that's smart.
It gives the administrator a very basic command prompt, just enough functionality to establish a connection, download a fresh, uncorrupted iOS image over the network into Flash, and recover the system.
That is literally the architecture of survival. Now, let's talk about how we actually interact with this architecture. Because if I'm a new IT grad stepping into a freezing cold, humming server room, and I plug a console cable into the back of a Cisco router, I am not greeted by a friendly graphical user interface, right?
Absolutely not. You are staring at a stark text-based command line interface, and this interface is rigidly structured around access levels.
Right.
From an operational and security standpoint, Cisco relies primarily on two access modes. When you first establish a connection and login, you are placed in user EXEC mode.
And I can tell I'm in user mode because the prompt on the screen will show the name of the router, say router A, followed by a greater than symbol, right?
Yes, the greater than symbol. In user mode, you are heavily restricted. An administrator or an attacker who has managed to guess a basic password can only perform non-disruptive basic troubleshooting tests.
Like pinging another device to see if it is awake.
Exactly, or viewing very limited system information. You cannot change any configurations, and you cannot view the sensitive security rules. It is a strictly look but do not touch environment.
So if an attacker compromises a user mode account, I mean, it's bad, but it isn't game over. To actually take control of the fortress, they need to escalate to privileged EXEC mode.
Privileged mode is the keys to the kingdom. You enter it by typing the command enable and providing a secondary highly secured password.
And the prompt changes.
Yes. You know you are there when the prompt changes from a greater than symbol to # or pound symbol. In privileged mode, an administrator has full administrative access and can view or alter any aspect of the router's behavior.
And from privileged mode, you can drop down into sub-modes to make specific changes.
Right.
Like typing configure terminal puts you into global configuration mode, where changes affect the entire router. But if you only want to change the rules on one specific fiber optic port, you would enter interface configuration mode.
It is a highly nested logical hierarchy, and mastering that hierarchy is non-negotiable. Dr. H.Schuessler's curriculum emphasizes this because when you are under the pressure of an active cyber attack, you cannot be fumbling with syntax.
Right. You need muscle memory.
You need to know instinctively how to navigate these modes.
Let's run through some of the critical commands mentioned in the text and look at them not just as administrative tools, but as double-edged swords.
Sure.
If I am an ethical hacker conducting a penetration test, or just a malicious actor who compromised privilege mode, how do I use a command like show version?
Show version is often the very first command an attacker will run. It displays vital system information, the amount of memory installed, and crucially, the exact version number of the Cisco iOS currently running.
Which gives them the playbook.
Exactly. If an attacker sees you are running an iOS version from 3 years ago, they can immediately cross-reference that version number against public vulnerability databases.
They don't have to guess how to attack you. The router just told them exactly which known exploits will work.
It's essentially handing them the blueprint.
What about the command show iproute? We talked about routing tables earlier.
Show iproute prints the entire routing table directly to the screen. For an attacker, this is the map of the hidden city.
Wow.
It reveals subnets, internal IP addresses, and the gateways to other autonomous systems that the attacker couldn't see from the outside. It tells them exactly where the valuable databases are likely located and which path the router uses to get there.
Then there is show running config. This feels like the most dangerous command of all if it falls into the wrong hands.
It absolutely is. Executing show running config from privileged mode dumps the entire active configuration file onto the screen. Everything. This includes every access control list, every routing rule, and devastatingly, the passwords.
Wait, it shows the passwords.
Depending on how the router was configured, those passwords might be stored in plain text or hashed using weak, easily crackable algorithms like MD5. If an attacker gets the running config, they practically own the network.
Which perfectly sets up the administrative side of things. If a defender makes changes to secure the network, they must execute the ultimate save your work command, right? If you want your changes to survive a reboot, you type copy running config, startup config.
Yes. That command takes the live active configuration currently residing in volatile RAM and writes it permanently into the non-volatile NVRAM.
Moving the whiteboard into the filing cabinet.
Exactly. It ensures the architectural blueprint is updated in the vault. Forgetting that single line of text has resulted in catastrophic network outages when a router unexpectedly reboots and reverts to an outdated configuration from months ago.
So we have the gates established. We know how the router boots, how it stores its maps, and how an administrator commands it. But simply routing traffic isn't security. It is just logistics.
Right.
To actually defend the network, we need to tell the router who is allowed inside and who must be turned away. That requires access control lists.
Access control lists, or ACLs, are the foundational logic of network perimeter defense. In their simplest definition, an IP access list is a sequential list of permit or deny statements applied to IP addresses, subnets, or specific protocols.
Okay.
You apply these lists to an interface on the router, dictating what traffic is allowed to enter the interface or what traffic is allowed to leave it.
To conceptualize this, I imagine if I'm trying to lock down a highly sensitive network segment, say, the HR database holding employee social security numbers, just blocking a malicious IP address isn't enough.
Definitely not.
If an attacker manages to spoof the IP address of the CEO's laptop, a basic filter will let them right in. We need a system that evaluates traffic on multiple layers of context. Let's contrast how a standard IP access list operates versus an extended IP access list.
A standard IP access list is the oldest and bluntest instrument. It filters network traffic based on one variable only, which is the source IP address of the incoming packet.
Just the source.
It doesn't look at where the packet is going, what protocol it is using, or what application port it is trying to access. It acts strictly as a bouncer checking the city listed on an ID card. Oh, you originate from the 192.168.5.0 subnet. You are denied. You originate from anywhere else. Come on in.
That seems incredibly restrictive and almost dangerously simplistic for a modern corporate environment.
It is, which is why standard ACLs are rarely used for primary perimeter defense anymore. They're mostly used for internal traffic management or to restrict which IPs are allowed to access the router's management interface.
Makes sense.
The syntax is very straightforward. You would type access list 1 deny 173.1.0.0 followed by a wildcard mask, and then crucially, you must follow it with access list 1 permit any.
Let's pause right there because that permit any statement brings up one of the most critical concepts in firewall and ACL logic, the implicit deny.
Yes, the implicit deny is the invisible rule at the absolute bottom of every access control list. It dictates that if a packet of data is evaluated against every single rule in your list, and it doesn't match any of the permit or deny statements you explicitly wrote, the router will automatically assume the packet is malicious and drop it.
So by default, if it isn't explicitly allowed, it is denied.
Exactly. So if an administrator forgets to add that permit any statement at the end of a block list, the router will block the specific bad IP and then implicitly drop every other piece of traffic on the internet.
Completely isolating the network.
Completely.
I can feel the collective anxiety of every network administrator listening to this. It's literally a single line of omitted text that takes an entire corporation offline.
It happens more often than you think.
Now, because standard ACLs are so blunt, the industry moved to extended IP access lists. How much deeper does the inspection go here?
Extended IP access lists provide granular surgical control. Instead of just looking at the source IP, an extended ACL evaluates a massive combination of factors. It checks the source IP address, the destination IP address, the specific protocol being used, such as TCP, UDP, or ICMP, and the exact application port number the traffic is aiming for.
So an extended ACL isn't just checking your ID at the door. It's checking who you are, exactly which room in the building you are trying to reach, what language you intend to speak once you get there, and what specific task you intend to perform.
That's the perfect way to visualize it. A real-world configuration for an extended ACL might translate to permit traffic originating from the public internet using the TCP protocol destined for our specific internal web server IP at 10.1.1.50, but only if the traffic is attempting to connect to port 443 for encrypted HTTPS web traffic.
So it's very specific.
Very. If an attacker sends traffic from the internet to that exact same web server IP, but tries to connect via port 22 to establish an SSH remote management session, the extended ACL looks at the port number, sees it doesn't match the rule, hits the implicit deny, and drops the packet.
And the logic of how these rules are ordered is paramount. The router reads the access control list sequentially from top to bottom, right?
Yes.
It takes a packet, compares it to rule number 1. If there is a match, it executes the permit or deny action, and it stops reading the list. It does not evaluate the rest of the rules.
This is a concept known as first match logic, and it is exactly where incredibly dangerous misconfigurations occur, specifically the creation of shadow rules.
Walk me through a shadow rule scenario. Like, how does that happen?
Suppose a junior admin is tasked with blocking a highly malicious subnet from accessing a database, but they want to allow the rest of the company to access it. They open the ACL configuration. On line 10, they write a broad rule: permit any source IP to access the database. Then, remembering their task, on line 20, they write the specific rule: deny malicious subnet from accessing the database.
Oh, I see the problem. When the malicious packet arrives, the router reads line 10. The packet matches any source IP, so the router permits the packet and stops reading.
Exactly.
Line 20 is completely shadowed. The malicious traffic flows right in, and the administrator thinks they are secure because the deny rule is technically in the configuration file.
Precisely. The logic of an ACL must always flow from the most specific rules at the top down to the most general rules at the bottom. This requires meticulous programmatic thinking. Misconfigured ACLs are consistently one of the leading causes of perimeter breaches, which is why understanding the exact syntax and processing logic is a core pillar of courses like Dr. Schuessler's. You are not just configuring a device, you are writing the laws of physics for that network segment.
But routers and ACLs, as powerful as they are essentially just traffic cops looking at the outside of the envelope. They look at the headers. To truly secure the perimeter against sophisticated threats, we need to inspect the cargo inside the envelope. We have to move beyond the router and explore the evolution of firewall technology.
While routers direct the traffic, firewalls are the true guardians of the perimeter. A firewall's sole existence is dedicated to controlling access between a trusted internal network and an untrusted external network.
Okay.
And just like routers, we have to look at the physical deployment. We have hardware firewalls and software firewalls, and the choice between the two dictates the network's capabilities and vulnerabilities.
Let's start with hardware firewalls.
Right.
What is the architectural advantage here?
A hardware firewall is a dedicated physical appliance. It uses proprietary operating systems like Cisco's ASA software or Palo Alto's PAN-OS running on custom-built silicon chips known as ASICs.
Application-specific integrated circuits.
Yes. Because the physical hardware is engineered to do absolutely nothing else but inspect network traffic, it can achieve staggering speeds. It can process millions of complex rules per second with almost zero latency.
But there's a downside, obviously.
The downside is cost and physical limitation. If your company doubles its internet bandwidth overnight, your hardware firewall might not have the processing power to handle the load, and you are forced into a massively expensive hardware upgrade. You are locked into the physical limitations of the box. A software firewall, on the other hand, provides flexibility. Correct. A software firewall is an application installed on a general-purpose server running a standard operating system like Windows Server or Linux. The massive advantage is scalability. If you need more throughput, you don't buy a new firewall appliance. You simply add more RAM to the server or install additional network interface cards. But that flexibility comes at a severe security cost, doesn't it? I mean, if the firewall software is running on top of Windows Server, it is inherently tied to the vulnerabilities of Windows Server. That is the critical trade-off. A software firewall is only as secure as the underlying operating system. If an attacker finds a zero-day exploit in the Linux kernel or the Windows TCP/IP stack, they can crash the server or compromise it, bringing the firewall down with it. Wow. Furthermore, general-purpose servers are not optimized for line rate packet inspection, meaning software firewalls can introduce significant latency in high-traffic environments. Regardless of whether it sits on custom silicon or a Linux server, the core technologies these firewalls deploy are what really matter. The textbook dives into the evolution of these filtering mechanisms, starting with the most ubiquitous security feature in the world, NAT, or Network Address Translation. NAT is foundational to modern networking, both for security and for basic functionality. The core problem NAT solves is that there are simply not enough public IPv4 addresses for every device on the planet. With NAT, an entire corporate network containing 10,000 internal devices, laptops, servers, printers, can be hidden behind a single public IP address provided by the ISP. I always conceptualize NAT like the mailroom of a massive corporate skyscraper. The building has 5,000 employees, but they do not each have their own public street address. All the mail from the outside world is delivered to the single main public address of the building. Perfect analogy. When a package arrives, the internal mailroom, the NAT engine, looks at the package, checks an internal directory, translates the address, and routes it to floor 12, cubicle 4. The outside world never knows the internal layout of the building. They only interact with the mailroom. That is exactly how it works mechanically? And from a security perspective, NAT acts as an incredible camouflage. An attacker on the internet cannot directly scan a CEO's laptop or target a specific internal database because those internal private IP addresses literally do not exist on the public internet.
They can't be routed.
Right, they cannot be routed. The attacker can only attack the firewall's public IP.
But to handle thousands of connections simultaneously over one IP, NAT relies on a highly dynamic subset called PATE, or Port Address Translation. How does PATE mathematically manage that traffic?
When an internal user opens a web browser and connects to a server, the firewall takes their internal IP address and translates it to the company's single public IP. But to keep track of that specific session, the firewall assigns it a unique randomized source port number, say, port 45,000. It records this mapping in a translation table.
So the firewall remembers internal IP 10.1.1.5 is currently communicating with the outside world using public IP 203.0.1113.1 on port 45,000.
Yes. When the external web server replies, it sends the data back to the public IP on port 45,000. The firewall receives it, looks at its translation table, sees that port 45,000 correlates to internal IP 10.1.1.5, reverse translates the packet header, recalculates the checksums, and forwards the data to the correct internal user.
Wow.
P8 is what allows thousands of employees to browse the web simultaneously without their traffic getting mixed up, all while completely obscuring the internal network topology.
So NAT and PAT hide the map. But hiding the map doesn't stop an attacker who is just trying to kick the front door down. To actually inspect the traffic knocking on the door, firewalls use packet filtering. The textbook distinguishes between stateless and stateful packet filtering. Let's look at the mechanics of stateless first because it highlights a massive vulnerability.
Stateless packet filtering is the oldest form of firewall technology, and it operates very much like the access control lists we just discussed. It evaluates each packet in a vacuum, relying strictly on the information in the packet's header, the protocol, the source IP, the destination IP, and the port numbers.
Okay.
The critical flaw is the word stateless. It has absolutely no memory, it does not remember the packet that arrived a millisecond ago, and it has no concept of an ongoing conversation.
Which makes it incredibly gullible. If I'm an attacker, I don't need to establish a real connection. I can just spoof an IP address, craft a malicious packet that claims to be part of an ongoing conversation, and throw it at the firewall. Because the stateless firewall has no memory of the conversation starting, it just looks at the header, sees the IP and port are technically allowed, and lets the malicious packet right through.
Highly gullible.
Yeah.
Stateless firewalls are trivial to bypass using IP spoofing, and they are highly susceptible to denial of service attacks because they process every single junk packet individually, consuming massive CPU cycles.
Right.
To solve this gullibility, the industry developed SPI, or Stateful Packet Inspection.
SPI changed the entire paradigm of network defense. How does SPI introduce memory and context into the firewall decision-making process?
SPI tracks the actual state of a network connection. It maintains a highly dynamic mathematical ledger in its RAM called the state table. This table records the precise life cycle of every single two-way connection traversing the firewall.
Walk me through the mechanics of how the state table evaluates a standard web connection. How does it know the connection is legitimate?
It meticulously monitors the TCP three-way handshake. When an internal client wants to communicate with an external web server, the client sends a synchronization packet, a SYN.
Okay, the SYN.
The SPI firewall sees this, allows it out, and creates a pending entry in its state table. The external server replies with a SYN ACK acknowledging the request. The firewall verifies this reply, matches the pending entry, allows it in, and updates the table. Finally, the internal client sends an ACK acknowledging the server.
The handshake is complete.
Yes. Only at this exact moment does the SPI firewall update the state table to mark the session as established.
The genius of that is how it absolutely shuts down spoofing. If an attacker tries to launch a port scan, like an Nmap-X man scan, or just blasts rogue data packets at the firewall claiming to be returned traffic from a web server, the SPI firewall looks at the state table. It sees there was no SYN, no SYN ACK, no established handshake. The packet is instantly recognized as illegitimate and dropped into the void.
Precisely. SPI ensures that incoming traffic is only permitted if it is a direct, legitimate response to a request originating from the inside, or if it perfectly matches a predefined rule allowing a specific type of inbound connection. It is mathematically rigid and incredibly secure at the network layer.
But attackers are relentlessly adaptable. They quickly realized that trying to sneak rogue packets past an SPI firewall was impossible, so they changed their tactics. They stopped trying to break the handshake and instead started hiding their attacks inside legitimate, established, perfectly legal web traffic.
They disguise a bomb inside a standard shipping container.
Yes. And this brings us to the highest layer of firewall defense discussed in the chapter application layer inspection.
This was the necessary evolution. An application-aware firewall, often deployed as a way for web application of firewall, moves significantly higher up the OSI model than a traditional SPI firewall.
Oh, so?
Well, SPI ensures the packet came from the right place, completed the handshake, and is going to the correct port. But it stops there. It doesn't care what the data actually is. Application layer inspection opens the shipping container and examines the payload to ensure the traffic actually behaves like the protocol it claims to be.
So an attacker establishes a perfect TCP handshake with a corporate web server on port 80. The SPI firewall says, "Looks great, authorized connection." The attacker then sends an HTTP POST request, but inside the data field of that request, they hide a malicious SQL injection payload, like OR11, designed to force the backend database to dump all its user credentials.
An SPI firewall would wave that packet right through because the envelope looks perfect, but an application-aware firewall intercepts the packet, reassembles the payload, and evaluates the HTTP syntax. It analyzes the specific commands being sent to the web server.
And catches the SQL injection.
Exactly. It recognizes the SQL injection signature hidden inside the web request, terminates the session instantly, and logs the attack.
Many of these application layer firewalls operate as proxies, right? They completely sever the direct connection between the attacker and the server.
Yes. A true proxy firewall is the ultimate intermediary. When an external client tries to connect to an internal server, the firewall intercepts the connection and answers on behalf of the server.
Right.
The firewall then establishes a completely separate second connection to the internal server. It takes the data from the client, inspects it at the application layer, and if it is safe, passes it across the gap to the server. The external client never actually touches the internal server. It is a brilliant, highly secure architecture.
So we have built this incredible multi-layered fortress. We have enterprise routers directing traffic, complex access control lists, checking IDs, NAT hiding our layout, SPI tracking the state of every connection, and WAFs opening the payload to inspect the application data.
We're pretty locked down.
We are. But here we arrive at the central paradox of corporate network security. Businesses want the public to interact with them. They want customers to visit their websites, log into their customer portals, and send emails to their employees. You cannot put a solid brick wall in front of an e-commerce company.
Right, that defeats the purpose.
So if firewalls are the walls, what happens when you want the public to interact with you without letting them inside the fortress?
That paradox is solved through architectural design, specifically Section 4, the network lobby, technically known as the demilitarized zone, or DMZ.
The DMZ.
Yes. You absolutely cannot place a public-facing web server or an email server inside your highly secured internal network, because no matter how good your WAF is, web servers have software vulnerabilities. If an attacker manages to exploit a zero-day flaw in your web server software and breaches it, and that server is sitting on the same internal network switch as your domain controllers and employee workstations.
They have a staging ground right inside the fortress. It is game over.
Precisely. But you also can't leave the web server completely unprotected on the raw, unteamed internet, because it will be compromised in a matter of minutes by automated botnets. So you build a lobby, a highly controlled halfway point.
A demilitarized zone is a small, isolated perimeter network that sits strategically between the public internet and your private internal corporate network. It is designed to house the resources that a company explicitly wants to make available to untrusted internet users, typically web servers, email exchange servers, and external DNS servers.
Exactly, and the textbook provides some fantastic visual storytelling here regarding the actual architecture of a DMZ. While you can build a DMZ using a single firewall with 3 network interfaces, the most robust enterprise-grade way to build this is using a 2-firewall setup. Let's walk the listeners through visualizing that flow of traffic. Imagine tracing a packet from the outside in. On the far left, you have the wild internet. The packet travels toward the company and hits the first firewall, the perimeter firewall. This firewall is relatively permissive. It is configured to allow standard web traffic on ports 80 and 443 to pass through, but it blocks obvious noise and basic attacks.
Okay, so it's a basic filter.
Right. Once the packet passes through this first firewall, it enters the DMZ, the lobby. This is where your web server resides. The packet reaches the server, and the customer views your website.
So the public can access the web server, but they had to pass through an initial security checkpoint to get there. They are in the building, but they are contained.
Contained is the key word. Because behind those servers, on the far right side of the DMZ, sits a second firewall. This internal firewall is the real vault door.
The heavy-duty one.
Exactly. It stands strictly between the DMZ and your actual internal corporate network, where your sensitive databases and user workstations live. The ACL rules on this second firewall are incredibly draconian. It explicitly blocks all traffic originating from the internet. It only allows very specific, highly restricted traffic originating from the DMZ servers to enter the internal network.
Like allowing the web server to query an internal database on port 1433, but absolutely nothing else.
Exactly.
So if an advanced persistent threat actor manages to bypass the perimeter firewall, exploit the web application, and completely compromise the web server in the DMZ, they are still physically and logically trapped in the lobby.
They do not have access to the internal network.
They still have to figure out how to breach a completely separate, likely entirely different brand of firewall with much stricter rules just to get a foothold inside the actual company. It is a textbook definition of defense in depth.
Exactly. You are forcing the attacker to navigate multiple heterogeneous layers of security, burning their time, resources, and zero-day exploits, all while generating massive amounts of log data that your defenders can use to catch them.
And the hardware that often sits at the core of these complex, multi-layered architectures is the Cisco Adaptive Security Appliance, or the ASA. The text mentions the ASA replaced the legendary older Cisco PIX firewall. What made the ASA such a dominant force in enterprise security?
The PIX was a fantastic stateful packet inspection firewall, but it was just a firewall. The Cisco ASA revolutionized the space because it was one of the first highly successful, heavily adopted unified threat management devices.
Ah, the UTM.
Yes. It didn't just track state. It integrated advanced intrusion prevention systems and sophisticated application layer inspection directly into the physical appliance. It allowed administrators to build those complex DMZ architectures, establish highly secure VPN tunnels for remote workers, and inspect application payloads all from a single management plane.
And from a career readiness standpoint, which is a major focus of Dr. Schuessler's curriculum, learning the ASA is a massive resume booster because the configuration syntax is heavily tied to the Cisco routers we discussed earlier.
It lowers the learning curve significantly for network professionals. If you know how to navigate a Cisco router using Enable for privileged mode, Configure Terminal for global config, and Showrun to view the active configuration, you can sit down at a Cisco ASA and immediately start navigating its interface. It uses the same fundamental command line logic.
There is a very interesting real-world operational detail the textbook points out regarding logging into these enterprise devices like the ASA. When an administrator establishes an SSH connection to a corporate firewall, they are almost always greeted by a massive, intimidating legal banner covering their screen before they even type a password.
Oh yes, the legal banners.
The text quotes a typical banner. If you are not authorized to access this network device, log out immediately. It feels very cinematic, almost like a keep out sign on a military base. But from a technical perspective, the banner doesn't stop anyone from trying to log in. So why is it mandatory?
It is not a technical defense. It is a strict legal defense. In the realm of cybersecurity law, specifically under statutes like the Computer Fraud and Abuse Act in the United States, prosecuting a cyber criminal for unauthorized access often requires proving intent and knowledge.
Oh.
The prosecution must prove that the attacker knew they were accessing a restricted system and did not have permission to be there.
Ah, so if a system just presents a blank login prompt, a clever defense attorney could argue, my client thought this was a public testing server, there was no warning that it was restricted corporate infrastructure.
Exactly. By explicitly stating, via a login banner, that the device is restricted corporate property, that all activities are logged and monitored, and that unauthorized access will be prosecuted to the fullest extent of the law, the corporation completely neutralizes that legal defense.
That is fascinating.
It covers the basis for prosecution, and it also establishes the rules of engagement for internal employees or third-party contractors accessing the system. It is a stark reminder that ethical hacking and network defense operate within a rigid, highly consequential legal framework.
Okay, so let's summarize where we are. We have the perimeter walls built with routers and SPI firewalls. We have the highly structured DMZ lobby. We have the state-of-the-art Cisco ASA hardware running the show.
The whole package?
But here is the terrifying reality for an IT director. Having the best walls and the best locks in the world means absolutely nothing if a junior admin installs the lock backward, or if someone accidentally leaves a window wide open by misconfiguring an access control list.
Human error.
Exactly. Which brings us to auditing the defenses. How do MIS professionals actually test this complex architecture to ensure it is configured securely?
You cannot just write 1,000 lines of configuration code, deploy it, and assume you are secure. The complexity of modern networks guarantees human error. You have to actively, continuously audit the configurations. And the absolute gold standard, the industry benchmark for secure configuration, comes from the Center for Internet Security, or the CIS.
The CIS benchmarks. What exactly are they? Are they just a list of suggestions?
They are far more rigorous than suggestions. The CIS benchmarks are globally recognized industry consensus documents developed by communities of cybersecurity experts. They detail the absolute best configuration practices on how and exactly why to securely configure a specific operating system, cloud environment, or network device. Right. For example, if you are deploying a Cisco router running a specific iOS version, there is a CIS benchmark document that gives you step-by-step, line-by-line instructions on which services to disable, what encryption algorithms to enforce, and how to structure your access modes to eliminate known vulnerabilities.
They are the ultimate peer-reviewed checklist for hardening a device against attack. But practically speaking, comparing thousands of lines of code manually against a massive 200-page PDF document sounds impossible.
It is exhausting.
Yeah, if you are an auditor staring at lines of Cisco configuration code at 4:00 p.m. on Friday, human fatigue guarantees you are going to miss a misconfigured port or an inverted ACL logic statement. Isn't there an automated way to handle this?
Thankfully, yes. Relying on manual human auditing for complex configurations is a recipe for a breach. The CIS offers a configuration assessment tool, or CISCAT. It is an automated software application available for both Linux and Windows systems.
How does it work?
An administrator runs the CIT tool against a target device, and the software ingests the entire configuration file, instantly cross-references it against the massive database of CIS best practices, and generates a detailed report highlighting exactly where the device's configuration deviates from the secure baseline.
So it highlights the exact line of code that is wrong, explains why it poses a risk, and usually tells you how to fix it. That is a massive time saver.
A huge time saver.
But even with a tool telling me my code is wrong, reading lines of text all day can lead to serious operational blind spots. Code doesn't show you the big picture. If I have 50 routers and a dozen firewalls, how do I comprehend the overall risk to the network? As a visual learner, I always wonder, isn't there a way to actually see the network's vulnerabilities? To look at a tactical map instead of a spreadsheet?
This is where the textbook introduces a truly fascinating enterprise-grade tool called Red Seal. Red Seal is a network risk analysis and mapping platform, and it solves exactly the problem of conceptualizing abstract risk. It turns thousands of lines of disjointed code into a visual mathematical model of your entire network.
Walk me through a scenario. How does Red Seal actually build this visual map?
Imagine the daunting task of mapping a Fortune 500 network. Red Seal automates this by ingesting the raw configuration files, the routing tables, the NAT rules, the complex ACLs from every single router, switch, and firewall across your entire global infrastructure.
Okay, so it takes all the rules.
Then it takes the results from your endpoint vulnerability scanners, like Nessus or Qualys, which detail every unpatched server, out-of-date OS, and software vulnerability existing on the endpoints.
So it has the architectural blueprint of the roads and the locks, and it has a status report on every single house in the city.
Exactly. Red Seal's analytical engine ingests all of this disparate data and utilizes advanced graph theory to generate a comprehensive, highly visual, interactive map of the network architecture. But it doesn't just draw lines between boxes. It calculates every mathematically possible path a data packet could take.
It calculates the attack vectors.
Yes. It visually shows you exactly how an attacker could traverse the network. For example, an IT director might look at the Red Seal map and see a glowing red path. The software demonstrates that if an attacker compromises a seemingly insignificant, low-level web server on the perimeter, which Nessus flagged as missing a critical patch, the current complex web of firewall rules and routing tables actually allows a direct, unimpeded path from that compromised perimeter server all the way into the internal network, terminating at the core financial database.
The administrators might have thought the database was secure because the firewall sitting right in front of it looked solid.
Right, but they missed a backdoor.
Red Seal mapped a backdoor route through an obscure, forgotten VPN tunnel connected to that vulnerable web server that bypassed the main firewall entirely. It turns millions of lines of code into a visual, tactical map of exploit paths. That is an absolute game changer for risk remediation.
It allows security teams to prioritize their efforts. Instead of trying to patch 1,000 minor vulnerabilities randomly, Red Seal tells them exactly which single configuration change will sever the primary attack path to their most critical assets.
That is incredible. So the walls are up, the DMZ lobby is structured, the configurations are audited by CISCAT, and the attack paths are mapped and mitigated by Red Seal. But a static defense, no matter how perfectly configured, is a dead defense. Firewalls only block what they are specifically told to block. They don't actively hunt for new threats.
No, they don't.
We need the security cameras, the alarms, and the armed guards. This leads us perfectly into the realm of active defense, covering intrusion detection systems, intrusion prevention systems, and web filtering. Let's start with the alarms, the IDS.
An intrusion detection system, or IDS, acts as the sophisticated security camera and alarm system for the network. While a firewall primarily concerns itself with access control checking the ID at the door, an IDS monitors the actual behavior and content of the network traffic as it flows through the environment, hunting for attacks in progress.
How does it know what an attack looks like? If a firewall uses access lists, what does an IDS use?
A traditional IDS relies on signature-based detection. It examines the packet payloads traversing a connection and compares the sequence of bytes against a massive, constantly updated database of known exploit signatures.
Like antivirus software.
It operates very similarly to how traditional antivirus software uses definition files to identify known malware. If the IDS sees a stream of network traffic containing the exact byte sequence of a known Apache web server exploit, it triggers an alert.
So the IDS security camera sees someone acting suspiciously in the hallway, recognizes their face from an FBI wanted poster, and triggers a massive alarm in the Security Operations Center.
Yeah.
But, and this is the critical limitation, the IDS doesn't actually tackle the intruder.
Correct. By design, a purely passive IDS is an out-of-band device. It receives a copy of the network traffic, analyzes it, sends an alert, and logs the activity. But it does absolutely nothing to stop the malicious traffic from reaching its target.
So the attack still happens.
The attack still happens, you just get a notification about it. That limitation drove the development of the IPS, or Intrusion Prevention System.
An IPS acts as the active armed guards.
Yes. An IPS possesses the exact same analytical capabilities as an IDS, but it takes the additional critical step of performing an active countermeasure to physically block or terminate the intrusion in real time.
So the camera sees the intruder, recognizes them, and the IPS automatically slams down the blast doors in the hallway, trapping the attacker before they reach the vault. If an IPS is so much better because it actively stops the attack, why would any company ever deploy a passive IDS? Why not just use IPS everywhere?
That is an excellent operational question, and it comes down to the risk of false positives. A false positive occurs when the system incorrectly identifies legitimate safe business traffic as an attack. If a passive IDS flags a false positive, it generates an annoying alert that an analyst has to review. But if an active IPS flags a false positive, it automatically blocks the traffic.
Oh, I see.
If your IPS mistakenly identifies the CEO's massive encrypted quarterly financial upload as a data exfiltration attack and drops the connection, you have just caused a self-inflicted denial of service.
Yeah, that's not good for your career.
No, it's not. Because of this risk, many organizations deploy an IPS in monitor-only mode, effectively acting as an IDS for weeks or months to tune the signatures and eliminate false positives before finally flipping the switch to actively block traffic.
That makes perfect sense. Now, just like firewalls, network architects have to decide where to place these detection and prevention systems. The textbook highlights the difference between network-based systems and host-based systems. Let's break down NIDS and EIPS first.
A network-based IDS, or IPS, referred to as NIDS, or NIDS, is designed to monitor activity across entire network segments. It acts as a microscopic vantage point. NIDS is usually connected to a switch via span port, receiving a mirrored copy of all traffic flowing across that switch. A true network-based IPS, however, must be installed in line with the network infrastructure, meaning the physical wire literally goes into the IPS appliance and out the other side. The traffic must pass through the IPS, giving it the physical capability to drop malicious packets instantly before they propagate further into the network.
And what about host-based systems, HIDSNs and HIPS? If we are already monitoring the network wires, why do we need software on the individual computers?
Because network-based systems have a major blind spot encrypted traffic, If an attacker establishes an encrypted SSL tunnel into a server, the NIDS just sees scrambled data flowing past. It cannot inspect the payload.
Right.
A host-based system is a localized layer of defense installed directly onto the specific machine you are trying to protect, usually a highly sensitive database or a critical application server. It operates deeply at the operating system or kernel level.
So by the time the data reaches the HIDS on the server has already decrypted the packet, allowing the host-based system to inspect the raw, unencrypted payload for malicious commands right before it executes.
Exactly. Furthermore, a HIDS monitors localized system behavior that a network sensor could never see. It watches for unauthorized modifications to critical registry keys, changes to core system files, or unexpected privilege escalations by local user accounts. It is a highly entrenched, granular layer of defense.
Now, we mentioned earlier that traditional IDS and IPS systems rely on signature matching the face to the wanted poster. But this creates a terrifying vulnerability for defenders. What happens when it is a brand new attack? A sophisticated zero-day exploit crafted by a nation-state that has never been seen in the wild and therefore has no signature in any database.
How does the system spot an invisible man?
Relying solely on signatures is a losing battle in modern cybersecurity. That is the role of the anomaly-based IDS. Instead of looking for specific malicious code, an anomaly-based system uses machine learning and statistical analysis to establish a comprehensive baseline of normal behavior for the network.
It learns the daily rhythm of the business. Yes. It spends weeks learning exactly what typical Tuesday morning traffic looks like. It learns the average bandwidth utilization, which specific ports are normally active, and precisely which internal servers regularly communicate with each other. It builds a complex mathematical model of normality.
And once that baseline is established, it just watches for deviations.
Precisely. If suddenly, at 3:00 a.m. on a Sunday, an internal HR server that usually only communicates with the local database suddenly initiates a massive encrypted file transfer over a non-standard port to an unknown IP address in Eastern Europe, the anomaly-based IDS does not need a signature file to know something is catastrophically wrong.
It just knows it's not normal.
Exactly. It flags the massive deviation from the baseline. Modern enterprise solutions mentioned in the text, such as McAfee Network Protection, Cisco SourceFire, FireEye, and the ubiquitous open-source tool Snort, all heavily integrate these advanced heuristic anomaly detection capabilities to hunt for zero-day threats.
I want to pivot for a second to the most vulnerable component of any network architecture, because an ethical hacker knows that breaking through an enterprise SPI firewall or a state-of-the-art anomaly-based IPS from the outside is incredibly difficult, noisy, and time-consuming. Why spend months trying to crack a Cisco ASA when you can just trick Bob in accounting into opening the front door from the inside?
The human element is, without question, the most vulnerable point in any security architecture. Attackers know this intimately. They frequently shift their focus from attacking the hardened perimeter servers to targeting the end-user workstations, primarily because those machines are usually allowed relatively free access outbound to the internet to conduct daily business.
And this is where web filtering becomes a mandatory layer of defense, because if a hacker can get an internal user to visit a compromised website, they bypass the inbound firewall rules entirely. The user requested the traffic, so the stateful firewall allows the malicious response back in.
Exactly. The text emphasizes the severe danger of drive-by downloads. This is a terrifying attack vector because it removes user interaction almost completely. A drive-by download involves a website visitor inadvertently downloading malicious code without their knowledge, simply by rendering a compromised web page in their browser.
Wait, the user doesn't even have to click a fake download now button or open a sketchy email attachment.
No. The attacker compromises a legitimate website, say a popular local news site, and injects an invisible one-pixel iframe into the code. When Bob in accounting visits the news site on his lunch break, his browser automatically attempts to load that hidden iframe.
And that's all it takes.
That's all it takes. The iframe contains exploit code targeting a known vulnerability in Bob's specific web browser version, or a flaw in a third-party plugin like Java or Adobe running in the background. The browser renders the page, the exploit executes silently, and the payload is dropped onto the workstation.
And once that payload, typically a Trojan or a backdoor, is installed on Bob's machine, the attacker has achieved a foothold inside the internal network. The Trojan then calls home to the attacker's command and control server to receive further instructions. And to the perimeter firewall, that call home just looks like standard outbound HTTP web traffic originating from Bob's computer, so it allows it out.
Which is precisely why robust web filtering is an absolute necessity. A corporate web filter does not just block employees from watching streaming sports or visiting social media. It is an active security mechanism. It constantly updates a massive database of categorized URLs.
Right.
It actively detects attempts by
It stops the drive-by download because Bob's browser is prevented from ever reaching the compromised site in the first place. But more importantly, if Bob brought an infected USB drive from home and plugged it in, the web filter acts as a containment field. When the Trojan tries to call home to the attacker's server to establish a reverse shell, the web filter recognizes the malicious destination URL and blocks the outbound communication, completely severing the attacker's remote control.
It is the ultimate babysitter for corporate internet access and a critical tool for disrupting the cyber kill chain. It might cause minor inconvenience when a user cannot reach a specific site, but the alternative is a catastrophic silent compromise of the internal network.
So we have the anomaly-based alarms ringing, the active IPS guards dropping packets, the web filter severing command and control beacons, and the Cisco firewalls logging every dropped connection. When the chaos starts, when the invisible siege turns into a full-blown breach, who is actually answering the call? Who looks at all this data? This brings us to our final major topic, Section 7, the command center and the trap. Let's talk about the operational reality of the SOC.
In a large, complex organization, normal system administration expertise is simply not enough to handle a live, active cyber attack.
Yeah.
You cannot rely on the Tier 1 IT help desk technician who just finished resetting a forgotten password or fixing a jammed printer to suddenly pivot and perform advanced threat hunting, damage assessment, risk remediation, and legal chain of custody data collection.
It's a completely different skill set.
Yes. Incident response requires a highly specialized mindset and a dedicated facility, a security operations center, or a SOC.
A SOC is essentially a permanent 247 command center whose members are dedicated solely to security monitoring and incident response functions. They are the digital firefighters of the organization.
They are, and their primary directive during and immediately after an incident is hunting for IOCs, or indicators of compromise. These are the digital fingerprints, the forensic artifacts left behind by attackers that definitively prove a system has been breached and reveal the attacker's methodology.
What does an IOC look like?
An IOC could be a specific, unusual log entry on a domain controller, a newly created administrative account, an unexpected registry key modification on a host, or a spike in outbound traffic to a known malicious IP address.
But hunting for those microscopic digital footprints across a corporate network consisting of 10,000 user laptops, hundreds of routers, dozens of firewalls, and massive cloud deployments sounds mathematically impossible for a human team. How do they aggregate and make sense of all that raw, disjointed information?
They rely on the central nervous system of the SIEM, security information and event management tools. A SIEM is the ultimate data aggregator and correlation engine.
Okay.
It automatically pulls raw log data continuously from everywhere in the environment. It ingests the router logs, the firewall state tables, the IDS alerts, the endpoint antivirus logs, the web filtering blocks and Windows event logs, and it pulls it all into a single, massive, centralized, searchable dashboard.
So instead of an analyst logging into 20 different devices to piece together a timeline, the SIEM does the heavy lifting.
Exactly. But it goes beyond just aggregation. It performs complex correlation based on predefined rules.
Give me an example of how a SIEM correlates disjointed events to uncover a stealthy attack.
Imagine an attacker trying to brute force their way into the network. At 2:0 p.m., the web filter logs a blocked connection to a known phishing site from a user's machine. At 2:05 p.m., the endpoint antivirus log on that same machine flags and deletes a suspicious executable file. At 2:10 p.m., the Active Directory server logs 10 failed login attempts for an administrator account originating from that exact machine.
Okay, I see where this is going.
Right. If you look at those events in isolation on 3 different consoles, they might just look like background noise. But the SIEM ingests all 3 events, analyzes the timeline and the source IP, connects the dots, and automatically generates a high-severity alert for the SOC analyst. Warning: probable compromised internal host attempting lateral movement and privilege escalation. It turns raw, disjointed noise into immediate, actionable intelligence.
That is the power of the SOC. Okay, I have been waiting for this final concept because it flips the entire defensive paradigm upside down. We've spent an hour talking about building impenetrable walls, blocking malicious traffic, closing ports, and keeping threat actors out. But what if we actually want to trick the hackers? What if we want to study their tools, waste their time, and catch them in the act? Let's talk about the deceptive art of the trap honeypots.
A honeypot is a brilliantly deceptive psychological tool. By definition, a honeypot is a vulnerable decoy computer or system placed on the perimeter of a network that contains fake information specifically intended to lure, deceive, and then trap hackers.
Let me push back on this conceptually, because I have a hard time wrapping my head around honeypots from a strict risk and liability perspective. We have exhaustively detailed how to lock down a network. Why on earth would an IT director intentionally deploy a vulnerable, unpatched server onto their perimeter? Are we just giving attackers a beachhead? If they compromise the honeypot, what stops them from pivoting and using that machine to launch attacks against the real internal network? It feels like inviting a vampire into your house just to see what kind of fangs they have.
It is a completely valid concern, and it highlights the operational risk of deploying deceptive technology. You invite the vampire in, but only because you completely control the physics of the room they enter. A honeypot is never connected to the production network. It is heavily isolated, usually placed in its own heavily monitored, quarantined VLAN, or even a completely separate physical network segment connected to the internet. If the attacker compromises the honeypot, they are trapped in a dead-end sandbox. There is absolutely no routed path for them to pivot to the real internal network.
Okay, so they are isolated, but what is the strategic value? Why do we want them there in the first place?
A honeypot is specifically configured by security professionals to have obvious, tantalizing vulnerabilities, maybe an outdated, unpatched version of an Apache web server, or an open FTP port with weak credentials. The primary goal is distraction and resource exhaustion.
Wasting their time.
Exactly. If a sophisticated threat actor is spending 3 hours trying to exploit a fake vulnerability on a decoy server, that is 3 hours they are not spending attacking your actual legitimate company resources. You are burning their most valuable asset, which is time. Some advanced honeypots act as tar pits, intentionally responding to network requests incredibly slowly to bog down the attacker's automated scanning tools.
It is sleight of hand. You're giving them a shiny object to play with.
Exactly. And to keep them engaged, the honeypot appears to hold highly valuable data. The security team populates it with fake, convincing corporate financial spreadsheets, dummy HR records with fake social security numbers, or pseudo source code.
Wow, they really go all out.
They do. The psychology is simple. If the hacker breaches the server and thinks they have found the jackpot, they will linger. They will stop looking for other ways into the network and focus all their energy on quietly extracting the fake data, believing they have pulled off a massive heist.
And while they are lingering, downloading gigabytes of fake spreadsheets, what is the SOC doing?
The SOC is watching every single keystroke. The secondary, and perhaps most vital goal of a honeypot is intelligence gathering. The honeypot acts as the ultimate early warning system.
Like a canary in a coal mine.
Yes. By studying exactly how the hacker breaks into the honeypot, the SOC team can capture their keystrokes, analyze the specific malware strains they upload, identify the IP addresses of their command and control servers, and learn what undocumented zero-day exploits they might possess. It allows defenders to study the attacker's exact methodologies in a safe environment, and then use that intelligence to write custom IDS signatures to harden the actual production network.
It literally turns the hunter into the hunted. The text mentions that this technology is evolving rapidly, too. You don't necessarily have to dedicate a $30,000 physical server to be a honeypot anymore, do you?
No, the landscape has shifted heavily toward virtual honeypots. Using advanced programming languages and virtualization software, a security engineer can spin up entirely fake, simulated servers or services in a matter of seconds. Tools like OpenCanary allow organizations to deploy dozens of these lightweight fake services across their entire network infrastructure with almost zero overhead.
So instead of one physical decoy server, you can scatter 100 fake database listeners, fake SSH prompts, and fake file shares across every subnet in the company. To an attacker running a network scan, it looks like an incredibly rich environment, completely saturated with vulnerable targets, but it is entirely a mirage.
A digital minefield. And the beauty of a virtual honeypot is its absolute silence. Legitimate users have absolutely no reason to ever interact with a fake database listener or an obscure, undocumented SSH port. Therefore, a honeypot should generate zero network traffic under normal conditions.
Which means, if a honeypot generates even a single alert, if anyone, anywhere, so much as touches that fake server, the SOC knows instantly, with 100% certainty, that an attacker or an unauthorized insider is actively probing the network. There are zero false positives. It's absolutely brilliant architecture.
Okay, let's zoom out and recap what we have covered today, because we have traveled deep through the entire complex architecture of a digital fortress.
We truly have covered the full spectrum of defense, from the enterprise routers that mathematically dictate the flow of packets to the access control lists that rigidly check the source and destination IDs.
And the firewall. Right. The complex, stateful packet inspection firewalls and application-aware WAFs that scrutinize the payload, the highly structured DMZ lobbies that isolate public traffic, the necessity of automated configuration auditing with tools like CISCAT and Red Seal, the active anomaly hunting IBS and IPS guards, the vital web filters preventing drive-by downloads, and finally, the psychological warfare and intelligence gathering of honeypots and the SOC.
The overarching takeaway here, the ultimate lesson for anyone entering the IT or cybersecurity field, is that security is not a product you buy. You cannot just purchase a magic UTM box from a vendor, plug it into the wall, and declare your corporation secure.
Never.
Cybersecurity is a deeply layered, highly coordinated operational strategy. It requires a profound understanding of how these vastly different systems interact, overlap, and sometimes conflict. The fortress holds strong against the invisible siege, not because of one thick perimeter wall, but because of an intelligent, adaptable, heavily monitored, and relentlessly audited defense in-depth system.
And that is precisely the core philosophy Dr. Schuessler's course emphasizes. It is about deeply understanding the symphony of these tools. It is designed to prepare students to walk into a modern security operations center, look at a complex network topology, and immediately understand the architecture they are defending.
It bridges that vital, often difficult gap between merely knowing the textbook definition of a firewall and possessing the operational capability to configure a Cisco ASA to actively intercept and stop a live intrusion in a corporate environment.
Exactly.
Which is exactly why we do these deep dives, to bridge that gap between theory and application. Thank you so much for joining us today in unpacking this incredibly complex world of network protection systems. As a reminder, if you found this analysis valuable, please like, subscribe, and share this deep dive. And again, absolutely check the description below for access to additional resources that you will find incredibly valuable as you navigate your IT and cybersecurity career.
We highly encourage you to explore the channel for other podcasts, playlists, videos, and classes to foster continuous learning. The technological landscape and the threat vectors change every single day. Your education, your mindset, and your skill set have to keep pace.
Absolutely. Continuous learning is the only way to survive in this industry. And if you enjoyed the depth of this analysis, be sure to check out the experts' other highly relevant series hosted right here on the channel, the Digital Forensics Podcast Series and the Network and System Security Podcast Series. They are phenomenal resources that dive even deeper into the mechanics of investigation and defense.
Thank you. Those series are designed specifically to complement exactly the kind of foundational architectural knowledge we built today.
Now, looking ahead to our next session, you will definitely want to join us next week for the 14th and final chapter from our textbook, Chapter 14, Hands-on Ethical Hacking Final Project. This is the culmination. This is where the rubber meets the road, and we take all the disparate theories we have learned, from cryptography and footprinting to firewalls and honeypots, and put them to the ultimate test in a comprehensive real-world simulation.
It is the absolute synthesis of everything we have discussed throughout the entire curriculum.
So, as we close out today's extensive deep dive into network protection, I want to leave you with a reflective question to consider regarding your own environments. Think about the invisible siege happening right now on your perimeter. If your network was breached today by an attacker who slipped past the stateless filters, bypassed the IPS, and avoided the honeypots. Wait, no, I shouldn't say that. I mean bypassed everything. Would your SIEM logs tell you the compelling, minute-by-minute forensic story of exactly how it happened? Or would you be left completely in the dark, standing in a compromised fortress, wondering where the walls fell? Master the attack, fortify the defense. Until next time, keep your hands on the keys and your network secure.